this is the second part of my 6-part series about simulating a time-varying temperature profile in a uniform bar. And in this part, we're going to derive a differencing scheme for calculating the time-varying temperature profile. So eventually, we're going to be implementing this in Python, but for now, we are just going to be deriving it on paper. Okay, so I have drawn or written out here, again, von Neumann's stability analysis, the partial differential equation, which is the basis of what we're doing. And then I also have a drawing of the bar that we keep mentioning. So you can see that the bar is split up into multiple sectors, and each sector is representative of an increment of position. And we can see that the entire length of the bar is delta x, which is the change in position. And the last increment is in -1, and the first increment is 0. And then we can also see that t is equal to 0, which we're going to say means that the time increment is equal to 0. So we can also draw this out for a time increment of delta t. And it's essentially the same thing. N equals 1 or n minus 1, 0, 1, 2, 3, dot, dot, dot. And again, this length is delta x. And we're going to do it a third time. And we'll say that this time increment is 2 delta t. Three. And n minus 1. And then we can say that just as an example, if we draw a dot on a certain position, we're going to identify that temperature at that position at that point in time as t n equals 0, because that's the time n, and j equal to 3, since that's the position. So if we were to draw a dot on this bar, it would be the temperature at 2 time increments and position 2. Okay, so now that we understand that, we can express this partial differential equation in terms of these t values. And to do that, we're again going to take the first derivative on the left-hand side and the second derivative on the right-hand side, but in terms of these t values. So on our left-hand side, since we are taking the derivative with respect to time, we'll have t at j at time n plus 1 minus tj at j, position j, at time n over delta t. And that's the first derivative of the temperature with respect to time. And that's going to be equal to the thermal diffusivity times the second derivative of the temperature with respect to position. So that's going to be Tj plus 1, since again, this is the derivative with respect to position, minus Tjn over delta x. And that is moving, that's the difference moving towards the right. And then we have to also accommodate for the difference moving towards the left, since this is a, and this is a second derivative. So we'll have Tjn minus Tj minus 1n. And again, that's going to be moving us towards the left over delta x. And again, this is the second derivative, so this is all over delta x. And so this is the finite difference of the derivative to the right, and this is the finite difference of the derivative to the left. So all we have to do now is simplify this, because we want the Tj n plus 1 value. We want an expression for that value. So that's pretty simple. Or can simplify. Well, we can simplify it. Well, and we can combine these values to simplify even further. And then if we just give the thermal diffusivity, change in time, and change in position values, if we merge those together and give them one big value, so let's just call it R, is equal to the thermal diffusivity times the change in time over the change in position squared, we can have an expression that we will use in the next part for coding. So our final expression is Tj at n+1, which this value is the new temperature to solve for at the n+1 time position j, is equal to Tjn, which is the a previous temperature at time n in position j. And the rest is pretty self-explanatory knowing those. Oops. And there you have it.